So picture this. It is the morning of March 3rd, 1994. You are way off the northwest coast of Western Australia.
Right, just completely surrounded by the Indian Ocean.
Exactly. Nothing but deep blue water everywhere you look. And drifting on that water is a vessel so massive, it honestly, it practically defies comprehension.
Yeah, the scale is just hard to grasp.
Right. It's the Australian Achiever. We are talking about a crude oil tanker weighing in at a staggering 127,575 tons.
It is basically a floating leviathan out there. I mean, you are dealing with a highly complex, really high-energy environment, and it's operating in one of the most unforgiving physical landscapes on Earth.
It really is. And today we are going on a deep dive into what happened aboard that ship. We've pulled a huge stack of sources for this one. Engineering teardowns, maritime history articles, and the main document anchoring all of this, which is the Australian Transport Safety Bureau Report number 67.
Yeah, that's the forensic autopsy of the event, basically.
Right. Our mission today is to unpack how a totally routine maintenance job, like literally just removing a water pump down in the belly of that steel beast, ended up resulting in the fatal electrocution of a young engineering cadet.
And it is a tragedy that fundamentally changed shipping forever.
It did. And we are going to look at this kind of like a true crime mystery, but for industrial engineering. Because the culprit here isn't necessarily a person, right?
Right.
It's this invisible, flawed system that essentially laid a trap for him.
Well, yeah, and when you read through this stack of research, you realize pretty quickly that the physical environment itself is, it's the primary contributing factor to that trap.
Oh, absolutely.
The engine room of a large-bore diesel tanker, and just for context, large bore means the engines have cylinders so big a person could literally stand inside them.
Wow.
Yeah, it's massive. And that engine room is a profoundly hostile place. You are dealing with ambient temperatures that easily exceed 40 degrees Celsius down there.
So that's well over 100 degrees Fahrenheit, just constantly.
Exactly. Plus oppressive humidity and this just constant bone-rattling vibration that degrades the equipment over time.
So I really want to spend a minute on the electrical setup in that specific environment, because looking through the engineering notes, it is completely alien compared to how electricity works in your house.
It is fundamentally different, yeah.
Right, because in a standard building, electricity flows through these insulated wires, and you have a dedicated copper grounding wire that is, physically driven into the earth outside.
Right, literally into the dirt.
Yeah. So if your washing machine shorts out, that rogue current travels down the wire and safely disperses into the ground. But out on the ocean, there is no earth to ground to. You are floating on a giant layer of insulating water.
Precisely. So marine engineers have to use the ship itself.
The actual hull.
Yeah. On a vessel like the Australian Achiever, which is generating massive amounts of power, specifically 440 volts of three-phase alternating current to run all that heavy machinery.
That's a lot of juice.
It is. And the entire steel hull, plus the superstructure of the ship, that all acts as the common ground return path.
Which means the ship is essentially just a giant floating wire. Like, if the insulation on a cable fails, maybe because of all that heavy engine vibration we talked about, and a live wire touches the metal casing of a machine, that casing is now fully energized.
Yep, it comes alive.
And anyone standing on the metal grating decks or holding onto a metal railing for balance, if they touch that energized casing, they complete the circuit. You basically become a fleshy resistor closing the loop.
I mean, that is a grim way to put it, but it is mechanically accurate. And this really brings us to the physics of marine electrocution, right? Specifically, Ohm's law.
Okay, break that down for us.
So Ohm's law is a fundamental law of physics. It dictates that the electrical current flowing through a body is equal to the voltage divided by the electrical resistance of that body.
Right.
Now, human skin naturally offers a pretty substantial amount of electrical resistance. It acts as a decent barrier, provided it is perfectly dry.
But wait, no one is perfectly dry in a tanker engine room where it's 40 degrees Celsius.
Precisely the opposite. The crew down there is constantly sweating, and moisture, particularly salty perspiration, is highly conductive. It drastically strips away the electrical resistance of the human body.
Oh, wow. So the sweat acts as a conductor.
Exactly. The sources note that in these specific engine room conditions, a person's resistance can drop down to just 1,000 ohms.
Which is incredibly low.
It is. At that level, touching a 440-volt circuit doesn't just give you a painful shock. It forces a massive, completely lethal surge of current directly through your body.
And the physiological response to that much alternating current is just terrifying to read about. The research details this thing called the no-let-go threshold.
Yes, that is a critical factor here.
So when a person encounters alternating current at just 15 to 20 milliamps, the muscles in the human hand and arm contract violently. The current literally hijacks your nerve system.
Yeah, your brain is no longer in control.
Right. The victim physically cannot release the energized object they are holding. Their own muscles are fighting against them, clamping down on the wire.
And because they are physically locked to the source, the current just continues to flow unabated. On a ship, the current often travels from the hand gripping the machine right down through the feet standing on the steel deck.
Straight through the chest.
Exactly. That path takes the electricity directly through the chest cavity, and it only takes about 50 to 100 milliamps to cause ventricular fibrillation.
That's when the heart muscle essentially shorts out, right? Like instead of pumping blood in a steady rhythm, it just sort of quivers uselessly.
Yeah, the heart's own delicate electrical signals get completely overwhelmed by the 440-volt surge. It leads to immediate and irreversible cardiac arrest, unless, a defibrillator is applied within minutes.
Which down in an engine room is practically impossible.
Exactly.
So the environment itself is just primed for disaster. You have this massive steel conductor, high voltage machinery, heavy sweating, and this terrifying physiological locking mechanism. That is the physical reality of the Australian Achiever on the morning of March 3rd, 1994.
It was a trap waiting to be sprung.
So let's look at the timeline of that morning, because the physics alone didn't cause this tragedy.
Yeah.
There were human decisions that armed the trap.
Right. So the morning begins normally. The ship is drifting off the coast, just waiting for a pilot to arrive to help them load crude oil. And a little before 10:00 a.m., the extra second engineer instructs an engineering cadet to remove the forward domestic fresh water pump.
They often call that a Megator pump, right?
Yes, the Megator pump. He tells the cadet to remove it so it can be hauled to the workshop for a mechanical overhaul.
And just for context for you listening, this pump draws fresh water and pressurizes it for the ship's bathrooms and galley. It is a really heavy piece of machinery,
right,
and it's driven by a powerful 440-volt electric motor.
And to safely work on a machine like that, it has to be completely physically and electrically isolated from its power source.
Makes sense. You wouldn't want it turning on while your hands are inside it.
Exactly. So the extra second engineer goes to the motor's starter panel. He switches the isolating switch and the selector switch to the off positions.
Okay, good so far.
But then he just stops there. He does not remove the main and control fuses from the panel. And he doesn't attach any sort of physical danger tag to the starter box to warn others that maintenance is underway.
Okay, I have to stop you there because I really don't understand this part of the report. If he is already standing right there at the starter panel, physically turning the switch off, pulling the fuse takes literally 5 seconds.
I know, it seems incredible in hindsight.
Right. Are the sources telling us he just skipped a 5-second step that ended up costing a life just to save a tiny bit of effort? Or was he genuinely that negligent?
Well, the ATSB report actually addresses this directly. The extra second engineer stated he assumed the job involved no electrical work.
Wait.
Yeah. Because he had instructed the cadet merely to undo the physical bolts, disconnect the drive belts, and physically move the pump. In his mind, simply turning the switch to off was totally sufficient for what he saw as a purely mechanical task.
But that assumption is so dangerous.
It is. Your frustration really highlights a massive vulnerability here, which is relying on personal assumptions rather than strict, documented isolation procedures.
So the cadet is left alone to do the job. But he runs into a hurdle. To do his work, or maybe because he wanted to double-check the electrical setup himself, which would be totally reasonable, the cadet goes back to that same starter box.
And these boxes are designed with a mechanical safety interlock.
Right.
You are not supposed to be able to open the front cover to access the wiring if the switch is in the off position.
Right.
It's a built-in safeguard to prevent anyone from accidentally touching live wires while they are turning the machine off.
But the cadet finds a workaround. The forensic investigation discovered he used a little spring steel clip, which was attached to his personal keyring, to essentially jimmy the lock.
Yeah, he used it to gain leverage, and he turned the isolating switch back to the on position just to bypass the interlock and get the door open.
This breaks my heart. He defeats the mechanical safeguard just to open the panel, completely unaware that by forcing the switch back to on, he is re-energizing the very circuits he just exposed.
It's tragic. Sometime around 10:39 a.m., as he is working with the panel open, his right hand comes into contact with a live terminal inside.
And we know the physics of what happens next.
We do. At 440 volts, with his electrical resistance completely compromised by the sweltering heat, the current instantly locks his muscles to the terminal.
But the thing is, this didn't happen in a vacuum, right? Like, the ship's internal systems actually detected the electrocution the exact second it happened.
They did. At exactly 10:39 a.m., an alarm sounds in the ship's machinery control room, and a dot matrix printer begins churning out a message indicating an earth fault on the 440-volt system.
Can you explain the mechanism of that alarm? Like, how does the ship actually know there's a fault?
Sure. So the ship's electrical monitors are constantly measuring the resistance between the live power lines and the steel hull. If current starts leaking into the hull, say, through a degraded wire, or in this tragic case, through a human body, the monitor detects that sudden voltage drop and immediately triggers the alarm.
Okay, so the fifth engineer is the duty officer in the control room at that exact moment. He hears the audible alarm, and he sees a flashing light on this massive console. And keep in mind, this console houses over 300 different alarm channels.
Right. It's a very noisy environment.
But he never checks the printer to read what the specific fault actually is.
No, he makes a fatal assumption. Earlier that same morning, he had responded to a different alarm, an earth fault on the 24-volt DC system.
Which is totally different from the 440-volt system.
Completely different. The 24-volt system runs low-power electronics like sensors and indicator lights. A fault there might just be a frayed sensor wire touching the hull. It was a very common, almost daily nuisance on this aging vessel.
Just background noise, basically.
Yeah. So when the alarm sounded at 10:39 a.m., the panel simply flashed a generic light. The fifth engineer assumed it was just that same harmless 24-volt sensor acting up again.
So he just hits the cancel button. He silences a lethal 440-volt earth fault alarm because he assumed it was just a routine annoyance.
Exactly. And it wasn't until 11:13 a.m., which is a full 34 minutes later, that the third engineer happened to just walk past the freshwater plant and found the cadet lying on the steel deck.
44 minutes later.
Yeah. The starter panel door was wide open, the switch was forced into the on position, and despite an emergency helicopter evacuation and prolonged resuscitation efforts, the cadet was pronounced dead.
It's just devastating. But when you read through the analysis, the fifth engineer's dismissal of that alarm wasn't just a random mistake or a brain fart. It was conditioned behavior.
Yes, absolutely.
When we look at how a modern high-tech operation fails so completely like this, we have to look past the individual mistakes and analyze the system that allowed those mistakes to line up perfectly.
And in safety engineering, this is best understood through James Reason's Swiss cheese model of accident causation.
Right. I've seen diagrams of this. Imagine multiple slices of Swiss cheese stacked up next to each other.
Exactly. Each slice represents a layer of defense in a complex system.
So one slice might be the technical safeguards, another is supervisory oversight, another is the procedural rulebook.
That's it. And usually, if a hazard slips through a hole in one slice of cheese, it is stopped by the solid part of the next slice. The error is caught before it does any real damage.
But occasionally, the holes in every single slice align perfectly. And that creates an uninterrupted path for a hazard to cause a catastrophe.
Exactly. So if we map this model to the Australian Achiever, the first slice was the technical layer. The physical equipment allowed a determined person to defeat a safety interlock with a simple keyring.
And the second slice was the procedural layer. There was absolutely no formal written requirement to physically remove the main fuses or place a warning tag on a machine before starting maintenance.
Right. It was left entirely up to the extra second engineer's personal discretion. Which leads us to the third slice, the supervisory layer.
Right, the cadet being left alone.
Yes. A junior cadet was instructed to dismantle heavy machinery without any direct oversight. And this really touches on the extreme power distance present in the maritime industry in the 1990s.
Tell me more about that, because that culture seems wild today.
Well, the hierarchy on a ship back then was absolute. A young cadet simply wouldn't feel empowered to question a senior engineer's methods or, demand that the fuses be pulled first. You just did what you were told.
Wow. Okay, so the final slice of cheese lining was the fifth engineer hitting the cancel button on that alarm. And if you look at the wider history of the Australian Achiever, you realize that his reaction was actually a symptom of a much deeper rot.
Oh, without a doubt. To fully understand why that alarm was ignored, we really have to look back to November 1992, which was about a year and a half before the cadet died.
Right.
The exact same ship suffered a catastrophic fire in its waste heat boiler.
Yeah, I read ATSB Report 46, which covers that fire, and it is staggering. This wasn't just some small trash can fire that they put out with an extinguisher.
Not at all. It burned out of control for 39 hours. The situation in the engine room was so severe that the crew couldn't even reach the actual seat of the fire.
Because of the heat.
Yeah, they were forced to use a tactic called boundary cooling. That's where you essentially just spray thousands of gallons of water onto the adjacent steel bulkheads and decks just to keep the heat from spreading to the rest of the ship.
That sounds terrifying.
It gets worse. The fire inside the boiler burned so intensely that the steel tube banks reached fusion temperatures and literally melted together.
But the truly shocking part of that report isn't even the 39-hour fire itself. It is the root cause. The engineering teardown notes that this massive waste heat boiler had been suffering from severe tube wastage for 4 to 6 years prior.
Tube wastage. Yeah, that's an engineering term for when the metal tubes inside the boiler literally rust, thin out, and corrode away over time due to neglect.
So the shipping company had left a major, highly volatile piece of engineering equipment in a state of known disrepair for half a decade.
Yes. Which begs the question, right, how does a 1992 boiler fire connect to a 1994 electrocution?
Exactly. And the sources point out that it perfectly illustrates this sociological concept known as the normalization of deviance.
Normalization of deviance.
Yeah, I've heard that phrase tossed around in discussions about, like, the Space Shuttle Challenger disaster. But what does that actually look like down in the engine room of an oil tanker?
So it happens when a clear deviation from proper safety rules becomes so common and so routinely ignored by management that the crew unconsciously accepts it as the new normal.
Oh, I see.
If a shipping company's upper management demonstrates that leaving a major boiler broken for 5 years is acceptable business practice, they send a very clear psychological signal to the crew. They are saying substandard is fine.
Wow, it lowers the bar for every other operation on the ship.
Exactly. It's like the ship's safety culture was eroding from the inside out, completely invisible from the surface until the hull finally breaches. If the company ignores the massive boiler, the crew is going to start ignoring the smaller things.
That makes so much sense. They stop being rigorous about electrical insulation testing. They don't bother formalizing isolation procedures.
Yep. Over time, the crew becomes completely desensitized to danger. A minor electric shock or a constant 24-volt nuisance alarm on the board, that just becomes accepted as the background noise of doing the job.
So the fifth engineer didn't dismiss the fatal 440-volt alarm out of negligence or, like, malice. He dismissed it because the ship's deeply compromised culture had systematically trained him to ignore warnings.
Exactly. The cadet's fate was essentially sealed long before he ever stepped on board, simply by a corporate culture that had stripped away all the safety margins.
That is heavy. But because the industry eventually realized that replacing one broken pump or, firing one engineer wouldn't fix a fundamentally broken culture, the entire global maritime rulebook had to be rewritten.
It really did. ATSB Report 67 didn't just sit on a shelf somewhere. It catalyzed a massive structural overhaul of how global shipping operates.
This was the end of the era of seaman's luck, wasn't it? The end of the informal verbal agreements where a senior officer just says, hey, I flipped the switch, you're good to go.
It was the absolute death knell for informal maintenance. This tragedy was a primary driver for the mandatory global adoption of the International Safety Management Code, or the ISM code, which was fully rolled out by 1998.
Okay.
The ISM code made informal maintenance strictly illegal.
So how does that actually look in practice today? If a cadet needs to remove that exact same water pump tomorrow morning, what is the process?
Well, it is heavily bureaucratized now by design. First, a formal written risk assessment must be generated. Then the chief engineer has to issue a written permit to work.
Okay, a lot of paperwork.
Lots of paperwork. And crucially, the crew must execute a physical lockout-tagout procedure, which requires a signed isolation certificate.
So it's not just flipping a switch anymore.
Not at all. Today, the engineer would turn the switch off, physically remove the fuses, and then place a physical padlock on the starter box door.
Wow, an actual padlock?
Yes, and the key to that padlock goes into a lockbox, and the person doing the maintenance, the cadet in this case, holds the master key. The machine physically cannot be re-energized until the maintenance worker personally signs off that they are clear of the equipment.
That is a massive shift. The sources also detail a major change in how the industry handles warnings and education too, right? We moved entirely away from the trial by fire, on-the-job learning that put this cadet in harm's way.
The training landscape was completely revolutionized. Today, engineering cadets spend hundreds of hours in shore-based high-voltage simulators.
Like flight simulators, but for engines.
Exactly. They learn the intricate step-by-step procedures of fault finding and electrical isolation in a digital environment. So a mistake results in a flashing red screen, not a lethal shock.
That's incredible.
And the industry also placed a strict legal duty of care on training officers aboard ships. Cadets are now legally recognized as learners who must be actively supervised, not just an extra set of hands to do the dirty work.
And the ISM code completely changed the culture of reporting, too. We talked about how crews used to just shrug off a minor shock or a nuisance alarm as part of the job.
Right. Under the ISM code, the reporting of near misses became absolutely mandatory.
Near misses?
Yeah. If a crew member gets even a minor tingle from a piece of equipment today, it must be reported as a non-conformity. The company is legally obligated to investigate and fix that latent hazard before it evolves into a fatal one.
But, laws only work if they are actually enforced. And from what I read in the maritime history articles, the real enforcement didn't actually come from government regulators. It came from the oil majors, companies like BP, Shell, and Exxon.
That's right. The oil majors realized that a single catastrophic failure, whether it resulted in a massive oil spill or a crew fatality, that could destroy their brand and expose them to massive liability.
So they took matters into their own hands.
They did. They created the Ship Inspection Report Program, which is known as the SIRE vetting system.
How does the SIRE system actually force compliance, though?
By hitting the shipping companies where it hurts the most, which is their wallets. The oil majors began sending their own independent, highly trained inspectors onto these tankers before they would ever agree to charter them.
Oh, so they gatekeep the work.
Exactly. These inspectors comb through the ship's maintenance logs, they test the crew on lockout-tagout procedures, and they audit the entire safety culture. If a ship's electrical safety records are poor, or if they find that alarms are being ignored, the oil major simply refuses to hire the vessel.
And a ship that cannot get chartered is a ship that loses millions of dollars.
Precisely. Financial survival suddenly required absolute safety compliance.
If you step back and look at the sheer scale of these changes, we're talking about taking an entire global industry that operated a bit like the Wild West, relying on individual grit, assumptions, and this rigid hierarchy, and transforming it into an environment that mirrors modern commercial aviation.
It really is a similar leap.
It became a world of strict checklists, redundant physical lockouts, and most importantly, corporate accountability.
The legacy of the Australian Achiever incident is the definitive proof that you simply cannot separate individual outcomes from organizational culture. When a system is stripped of its defenses, human error becomes fatal.
We started our deep dive drifting on a 127,000-ton steel conductor out in the Indian Ocean. And we've seen how the brutal physical environment, the heat, the sweat, and the unforgiving physics of alternating current created this lethal trap for a young cadet.
And we examined how the normalization of deviance stemming from years of neglected maintenance like that 1992 boiler fire just totally eroded the crew's perception of danger.
Right. It created a reality where safety protocols were viewed as optional and critical alarms were treated as daily nuisances.
And we watched every single layer of James Reason's Swiss cheese model fail simultaneously. An unpulled fuse, a bypass mechanical interlock, an unsupervised learner, and a silenced warning.
It took the perfect alignment of all those systemic failures to turn a basic water pump repair into a watershed tragedy that fundamentally rewrote the rules of the sea.
As the foundational safety texts remind us, safety is not merely the absence of accidents. It is the active, continuous presence of defenses.
Which leaves us with a quiet, lingering question about the environments we all operate in every day. On the morning of March 3, 1994, the fifth engineer silenced a fatal 440-volt warning because he had simply gotten so used to the noise of a broken system that he couldn't hear the real emergency.
It's a sobering thought.
It is. We might not work in the sweltering engine room of an oil tanker, but we all navigate complex systems. So it's worth asking ourselves, what nuisance alarms are we currently ignoring in our own lives or institutions just because we've grown accustomed to the background noise? And what might the true cost be when the real emergency finally sounds?